This is the notebook for the videos, Neural Nets Explained Without Calculus, Parts 1 and 2. In this notebook, we will examine the underlying mechanism of how any neural net model learns. Knowledge of calculus is not required to understand this. We will examine a toy model that learns the value of just one number from training data. This number is then used to make predictions for input the model has never seen during training. The input to the model is the number of rooms in a house, and the model output is the price of the house. The toy model function transforms input to the output using this one number, m. It simply scales the input by multiplying it by m to produce the output. The objective of the training is to learn this number so that the model predictions are as close as possible to the true values. Let's assume we are given a training dataset of say 10 homes with the number of rooms and prices for each home. We start off with a random value of m in the model function. We feed in all the rooms as input, and the model outputs its price predictions. We then compare the predicted price with actual price, and see how far off the model is in its predictions. We find this by subtracting the predicted price from the actual price of a home, and square that value to avoid negative values. We then find the average error by dividing this value by the total number of training samples. This is the model error or loss function for our toy model. Note, in the loss function, the x and y values are all constant, they are training data. The only changeable quantity is m. Also note the model error is a single number, and is the average error of the model, across all training data points, for a particular value of m. We want to modify the value of m so that the model error is minimized. The plot of the loss function offers a solution to reduce error by modifying m. M is plotted on the x-axis, and the loss on the y-axis. For instance, if we are at point A in the figure, and add a small amount to m, the loss goes down and we end up at point A prime. The slope, or the gradient of the line, connecting these 2 points, is essentially the change in loss for unit change in m. The gradient is negative at A, because the function value went down. On the other hand, if we are at point B, and add a small amount to m, the loss goes up, and we end up at B prime. So the gradient of the line connecting B and B prime is positive. Essentially, gradient gives us 2 pieces of information. First, it gives us the direction of the function response to a small increase in the input. That is, does the function go up or down when we increase the input a little? Secondly, gradient also gives the magnitude of the function response to a small increase in the input. For example, the function response at A is less than the response at B in the figure, for the same increment of the input. We can use the information gradient gives to move up or down the loss function curve. To move up the loss function curve from a point where m is say, x, just add a small fraction of the gradient at that point to x. Conversely, to move down the loss function curve at a point where m is x, just subtract a small fraction of the gradient at that point from x. This observation is true regardless of the shape of the loss function and the initial value of m. That is, we can start with any random value of m, and still walk downhill to the minimum loss value. We will use this observation to minimize the error in our model. We will simply subtract a small portion of the gradient at m from the current value of m. We keep doing this iteratively to reduce the loss. The code below creates a synthetic dataset for training our toy model. We will skip the training code for now, and look at the visualizations to get a feel for the training process. Before training, the model's price predictions with the randomly chosen value m is way off from the actual prices. As training progresses, the value of m is updated to reduce this difference. At the end of the training, the model predictions have significantly improved. We will now examine the code to see how the model prediction improves over iterations. We start off with the model function, which takes as input m, the line slope, and an array containing all the room counts in the training data. This function returns an array of predicted prices. In this toy model, we do 100 iterations over the training data to learn the value of m. We start off with a random value for m. In the learning loop, we predict the price of homes with the current value of m. We then calculate the average error across all the training points. The error is the squared difference of the true price and the predicted price. Recalling the figure we saw initially, we now have the coordinate of the point A, which is the current value of m, and the average error for this value of m. We now increment m by a small step. This gives us the x-coordinate of point A prime. We recompute the average loss again to get the y-coordinate of point A prime. We can now compute the slope, or the gradient, between these 2 points. we subtract a small fraction of this gradient from m. This fraction is called the learning rate. We chose this value up front. Choosing a large value for this will cause large updates to m, and we may step past the lowest point by taking a large step, making the training unstable. We can see this by setting learning rate to say 0.05 and training the model. On the other hand, setting the learning rate to too small a value will make the updates to m small, so the model will take longer to get to the optimal value of m. Even though we used a constant learning rate throughout the training, given the gradient of the loss function was steep initially, we did large updates to m in the beginning. After that we did smaller updates, as m approached the valley of the loss function, where the lowest error lies. We then repeat the training loop with the new value of m. In this toy model, we only had one number to learn. In future notebooks, we'll see how the same approach can be used to train a model which has more than one number to learn. This learning approach applies to any neural net model. That is, even a model with billion learnable numbers adopts the same approach. But in practice, we don't compute the gradient like we did in this toy model. It is inefficient, because during each iteration, we sent the training data twice for each value of m to compute the gradient. The gradient computation is not only inefficient in our toy model, it is an approximation of the true gradient. We can compute the gradient using calculus, without passing the training data through the model twice, for each value of m. Also, the computation of gradients is done efficiently, using the backpropagation algorithm. We will examine this in a future notebook. Another simplification made in this toy model is the update of the model parameter. We always updated the model parameter m with a constant fraction of the gradient. In practice, this update is done using an algorithm called gradient descent that decides what fraction of the gradient to use to step down the hill based on how steep the slope is at each step of the training. Regardless of these differences, this notebook illustrates the core idea in neural net training or learning. That is, finding an optimal setting of all the model parameters, or learnable numbers, so that the function in which they are embedded in transforms the training input to produce an output that is as close as possible to the corresponding training output.